Okay, now, my name is Jamal Ashraf, and then again, we talked about the linked list. What is the linked list in part one? How do we insert elements in part one? How do we remove elements in part two? Now we're going to be looking at the efficiency of the linked list for the list operation. So one of the things that we do in data structure, we want to check about the efficiency. On the previous videos, we talked about how to calculate the efficiency, the worst scenario, the best scenario, and we're going to figure out what's going to be. So let's look at the linked list and its efficiency. So if I want to go to element K of the linked list, I have to start from the beginning. Remember, I know where the head is, I know where the tail is, but I got to start from the head, or I can start with tail if I want to, and I got to keep going to each element of the list to find where I want to be. So I'm going to be looking at each one till I get to where I want to be. So when I'm adding and removing an element, we opted a couple of references in the constant number of steps. So as soon as I know where I am, if I want to add or remove, we just update our references. So we are not moving the whole object. It can be a huge object. We're just going to be updating the reference for it. So it's basically going to be just one operation either way. And that's going to be a big O of one, just one thing that we need to do. Now, so adding or removing is going to be operation one. Now, if I want to add to the end of the linked list, again, it's going to be operation one because I don't have to go through the whole list. I already know where the tail is. I can just go at the end and just add it to them. So one algorithm can be always add to the end of the list. That way you don't have to worry about it. And that's just going to be an operation. So we can use the tail if we have. If we don't have a tail, then we have to go through each element to get to the end of the list. If we have the tail, it's going to be just one. If we don't have a tail, it's going to go through the whole list. That's going to be operation, the big O N. So if the linked list keeps a reference of the last, in our case, we are talking about tail, as well as first, then adding to the end is going to be just one operation. Now, what about the removing? So we need to have a reference to next to the last element. So we need the previous element to be able to remove it. So for that, it takes n minus 1 to get to that element. And in general, it's going to take us the whole list. The worst scenario is the whole list. The best scenario is going to be just one. So the worst would be visiting each one of them to find the one that we're looking for. So in general, with the linked list, if we don't keep track of tail, we have to go through each element in the worst scenario to find something, to either find a location, to either add or remove an element. Okay, so I'm going to stop right there for the efficiency. We're going to come back and compare it with the doubly linked list. So the next one is going to be, I'm going to be talking about doubly. So it's a double linked list. So instead of one, we can go both direction. So instead of just singly linked list, it can go only to one direction. I cannot go back and forth, but the doubly linked list is going to go both ways. So I can go to left or right to find things a little fast. So I'm going to stop right here, and then we're going to continue on part 4 for doubly linked list.